GM everybody. Hello. Hey all, Yasin here. Hope you're having a great day. Make sure to say hi in chat. Excited day again, and we're going to be having Zhiyong Fang today, as we're going to be covering the introduction to Expander and GKR. Let me quickly invite Zhiyong on stage. Welcome on stage.
Hello everyone.
Right, we're ready for you to share your screen when you're ready. As always, everybody in the audience, please make sure to post your questions in the questions tab. It's on the bottom right side, and Zhiyong will be able to come back to them when he sees fit. For recordings, again, as always, you will be able to find these within the Hacker Pack. And this event is always recorded, and we'll make sure to add it in the next 24 hours. Zhiyong, over to you.
Okay, thank you for the introduction. So hi everyone. I'm Zhiyong from Polyhedra. So and today I'm going to give an introduction to Expander and GKR. So I mean the purpose of this talk is to give you some information and also hopefully get you more familiar with our system. So feel free to post any questions in the chat, and yeah, I will try to get back to it as soon as I can. Okay, let's get started. So I'd like to first give an overview of the GKR protocol. I think you must be familiar with it more or less, so I'll go over this real quick. So the GKR protocol is an argument system to prove circuit satisfiability. As shown in the example here, it's like the prover would like to prove an argument saying that I know some private input I1, I2, and I3 satisfying C of I1, I2, I3 equals to some specific output O of 1. GKR has several advantages and disadvantages. For example, it has no trusted setup. It benefits from its linear proving time. However, it also has some disadvantages, such as relatively large proof size and a linear verification time, which is a little bit more expensive than Planck-style proof system. So that was GKR. So what is Expander? It's our highly optimized GKR implementation. So the optimization can be divided into two parts. One from the implementation side, which includes a careful organization of fields, which includes we're trying to minimize the memory operations, including allocation, deallocation, and memory copy. And we also have recursion in our system in order to reduce the proof size and verification time. Beyond that, we also have several optimizations from the formulation side, which means we change the sum check equation a little bit in order to improve both the prover and the verifier. So we first change the formulation for the addition gate a little bit to allow arbitrary number of input instead of just 2. So we also enable single instruction, multiple data instructions to make best use of single core computation. And beyond single core computation, we use the MPI framework to enable multi-core collaboration. Beyond that, we also so GKR is designed for layered circuit from the basic definition. So we extend that definition to cross-layer circuit. That was created to the Virgo++ paper, and we integrate it here. Well, before we go into the details of these optimizations, I would like to give you a simple use case of the system. So if you've attended the previous lecture from one of our colleagues, you must have known the Expander compiler collection. But if you have not, it's totally okay. I'll just quickly go through it. So the Expander proving system is fully integrated into our compiler collection. So you can first declare a circuit which looks like this. Declare the input of the circuit and the output of the circuit. And then you can define the concrete computation of the circuit. And for here, it's a KCAG hash function. And after you successfully declare the circuit, you can generate some assignment and then put some correct values into the assignment and then call the prover, just like call the executor proof, which is relatively simple to use from the Expander compiler collection. Okay, so let's get back to the presentation. So you can use that directly in Rust from the Expander compiler collection, and you can also run the code as an independent repo where we list some instruction here. So you can specify your input circuit file with input witness file and the output file where you want to put the proof to. You can also specify the number of cores you use. So recall that we use the MPI framework. So we can call the MPI executor here to launch the prover in a multi-core fashion. So, okay. So this is a basic usage of our Expander system. Any questions? Okay, so let's continue. Let me give you some basic numbers about the performance of the Expander system. So for the KCAG function on this CPU model with 16 cores, we managed to prove around 10,000 to 15,000 per second on the GF2 field. And for the Merson 31 field, we managed to achieve a performance of around 3,000 to 4,000 per second. We also tried to instantiate our system with the VGG16 neural network. Currently, for a single core to prove a single inference of the network, it took around 2.5 seconds. Okay, so that's the high-level overview of our system. And next, I'm going to give some details in the implementation. So I will start with the recall that we have two types of optimization. One is the implementation, and the other is the formulation. I'll start with the implementation first. So we are using a lot of single instruction, multiple data instructions. So we introduce a lot of different fields other than the base one. So let's say we're using the Merson 31 as a base field. Due to the use of SIMD, we introduced a new field of Merson 31 times 8, which means we're performing the addition and the multiplication of Merson 31 field at the same time for 8 instances. Also, if you are familiar with the proving system, you may know that base field sometimes is not enough for security reasons. So there will be an extension field, which we call, which we use the degree 3 extension of the base field. And the extension field also have to deal with the SIMD usage. So we introduce additional field called Merson 31 extension 3 times 8. We are organizing the fields in such a structure for Merson 31 here. And we also have the same thing for the GF2 or shard, I mean, not sure, for the Bn field. You can easily see that the operation on this field is cheaper in the bottom and more expensive on the top. So the principle is to keep as many operations as possible in the base field. Yeah. So yeah, why this helps? So first, obviously, the base field operations are cheaper. And the second thing is we can carefully handling the interaction between different fields. Let me give you an example. So let's say we're doing the multiplication between Mersenne 31 extension 3 field and Mersenne 31 times 8 field. In the previous figure, it's the field from the left side and the field from the right side. So you can always extend them to the extension field and also SIMD extension field and perform the operation. However, that will be very costly. What you can actually do is just extend everything from the SIMD base field to SIMD extension field and then perform the operation Another example would be the addition between the Gallagher's field 2 and Gallagher's field 2 times 8. So recall that the addition is simple on Gallagher's 2 field is simply XOR operation. In this case, we're adding 1 bit bitwise to a 8-bit integer. While we can perform the operation faithfully, a trick would be just use an if condition to decide whether this bit is 0 or 1, and then output the. If it's 0, we can simply output the right-hand side by itself without performing any bitwise operations. Well, yeah, that completes the first optimizations of field organization. And the second one would be to minimizing the memory operations, including mostly it's allocation and deallocation. So recall that the GKR protocol consists of repeating sum checks. And we noticed that the repeating sum checks usually requires a similar amount of memory in each instantiation of the sum checks. So instead of just allocate the memory, performing sum check number 1, and deallocate the memory, instead of perform sequence of operations like this, we can pre-allocate the maximum required amount of memory at the beginning and only deallocate it at the very end, and just perform the sum check operations based on this allocated memory. While the computation costs do dominate, we noticed that the memory allocation and deallocation contributes a lot to the total running time, and that's why we try to use this approach. We also have a proof recursion mechanism to reduce the proof size and the verification time. So our motivation is to reduce the relatively large proof size and linear verification time. So the GKR, if you are familiar with GKR, you will know that it has a proof size linear to the depth of the circuit, and that's why it's relatively large. And the verification time is linear to the circuit size. So the question here is, can we simply do a recursion? If we have a growth 16 prover, it would produce a constant size proof and constant time verification. Can we simply use the growth 16 prover to verify the GKR proof and produce a much shorter proof? That way we can enjoy the good things from both sides. with linear proving time and constant proof size and constant verification time? Well, the answer is yes, but conditionally. We have some numbers for the recursive proving system. For here, we are proving a K-check circuit, which has around 800,000 gates. Well, unfortunately, the verifier circuit has a size of around 9 million, which does not make sense if we only prove a single K-check circuit and use it and use recursion to prove the GKR proof. Below is a table of, so we've finished the recursion and we have a reported number. Below we are trying to reason the number of gates in the verification circuit. So we can see in the recursion circuit, the hash used in the Fiat-Shamir functionality dominates the cost. It accounts for around actually more than half of the final verification circuit. And the right-hand side, these two parts are the actual computation running by the verifier, and they account for the other half of the verification circuit. So let's get back to the numbers, which is 800,000 versus 9 million. It won't make sense if the verification circuit is actually larger than the original circuit, because that way why just I simply run the growth 16 on the original circuit instead of run the growth 16 on verifying the GKR proof. So that's why we use batching. And that's why we use the batching technique. So intuitively, if we batch 16 proof, or probably 128 proof, the verification circuit size would roughly be the same, still around 9 million, but the original gates would be much larger. And then in that case, we do benefit from the proof recursion. Yeah. However, there are several problems to solve in recursion. One problem would be the Fiat-Shamir. So Fiat-Shamir itself is already probably a problem in GKR. And if we are using it for recursion, it may be an even larger problem. And we are actively investigating into the security problem of Fiat-Shamir here. Okay, so that finishes the optimization from the implementation side. Any questions here? Well, let me see. Is the Virgo paper the Virgo one by Dong Song? Yes, I think its name. Oh, okay. Zhenfei has already answered for me. Yes, thank you. Okay. Sounds good. So let's continue. Okay, so that finishes the optimization from the implementation side. We also have some optimizations from the formulation side. For example, below is the typical sum check equation, which you will see in the paper. Let me explain it a little bit. So the tilde here means they are multilinear extensions. The function v here is a multilinear extension of the gate values on a specific layer, say layer I and layer I plus 1. And the addition function here would be equal to 1 if the addition gate Z is connected. The addition gate Z in layer I plus 1 here is connected to the gate X and gate Y on layer I. So if you evaluate the left-hand side on all of the possible Z's, on the Boolean hypercube, you will find that the left-hand side actually equal to the right-hand side. It's basically a different expression of the circuit evaluation. Okay, so our first optimization on the formulation is to change the formulation for the addition function a little bit. So previously we have two input for the addition function, but it turns out we actually need one, and it's at least I think it's at least the same expressive as the previous one, because we're sum over all the gates from the previous layer. So why is this good? So here we only allow gates of fan-in 2, and by remove the variable y here, we are not limiting the expressiveness of the circuit. We are actually expanding it. We allow fan-in gates of addition gates of arbitrary fan-in numbers. And another thing is the prover would now finish the reduction of the variable x in the middle of the sum check. You can see that after reduce the variable x, the prover is able to send the claim for the next round, and only handle the remaining part without any values from the addition function. And even better, if the layer contains only the additional gate, we can completely avoid the second part. So avoiding half of the sum check reduction. Yes, so that's formulation of the additional gate. Another thing we introduced here is single SIMD and MPI instruction. So this basically allows for parallel execution of multiple GKR instances. So now we have variable. So previously we are proving a single circuit, and now we are proving multiple circuits at once. To account for the multiple instances, we introduce a new variable here. So in the multilinear extension of the circuit value, multilinear extension of the circuit values, we have an additional variable here, which is essentially saying that which instance are we in the parallel execution. To account for that, we also introduce a variable here in the sum check equation. We request these two variables to be the same in order for this EQ function to be 1. So recall that we are running a parallel instance of the same circuit, so the addition gate and the multiplication gate, which essentially describe the structure of the circuit, does not change here. However, the multilinear extension of next layer V of I here do introduce a new variable Q to specify which copy of the parallel execution they are in. The good point of this extension of the sum check equation allows us to use SIMD instructions on single core, and also allows us to use MPI parallel execution. You can think of the variable Q and variable R of P here accounts for both SIMD and MPI. It's more like the first a few bits account for the SIMD instruction, and the later a few bits accounts for the MPI parallel execution. One thing that was noting is that the variable Q here has a slightly higher degree, which is 3, compared to the previous formulation of X and Y both have degree 2 in the previous simulation. And of course, it also has degree 2 here, but the additional variable q has a degree of 3, which may cause some slight overhead. I mean, not overhead, some slight additional cost for the prover. So let's analyze the parallel execution in the best case. So if the log of n, where n is the number of parallelization, if it's negligible compared to the size of x and y, and if all cores have the same speed, this matters because, well, in the sum check protocol, we need to sync up after each sum check run. All cores would need to wait to the slowest guy before they are able to receive the message. So basically, all cores need to send their current round message to the root, and the root compute a fair shamir and then broadcast it to all the cores. So the slowest cores so all cores need to wait for the slowest one. And the third assumption would be we assume the communication cost is negligible. So based on these assumptions, we would have very good results. So almost no additional cost for the proving time, verification time, and proof size. Of course, this is not true in practice. So in practice, the prover has to pay a logarithmic of n cost for each layer of the circuit. And the verification time and proof size is also increased by logarithmic of n times logarithmic of n number of field of elements. For each layer of the GKR circuit. Okay, so that's for the parallel execution of the Expander system. We are also incorporating the cross-layer circuit into our system. So the intuition is that you have a value that would be relayed all the way from the input to the output. It would be great if we can add a cross-layer link to allow it to directly reach the output layer. That would significantly reduce the number of gates in the circuit. Of course, it would introduce some additional cost to the proving system. So in the paper, the Vego++ paper, they allow arbitrary circuit, arbitrary DAG circuit. But here we made some simplification where we only allow cross-layer additional gates to achieve a better balance between the proving complexity and the circuit size. So that's pretty much all I would like to say. And we have of course, we have a lot to do. So the first thing is, well, the cross-layer circuit, the Virgo++ implementation is still a prototype, and we need to integrate the cross-layer implementation into the product. And the second would be we're still implementing a lot of polynomial commitment scheme for the input layer. We now have a raw PCS, which actually does nothing, and also a coding-based polynomial commitment scheme. And we are actively incorporating the BiKZG for the BN field. And the third thing we would like to do is to integrate Expander to a system called ZK CUDA. Well, it's not something like proving the CUDA execution. It's a systematic proving system. You can think of as organizing the proving system, and let's see, how do you say? It's like organizing the proving system. You can use this proving system to prove this one. You can use that proving system to prove that one, and finally combine the proof. Yeah, a system like this. And the final thing is we would like to improve the recursion efficiency and also investigate the security of the system. Yeah, that's pretty much all. And any questions are welcome. And if you would like to contribute, yeah, it's warmly welcome. Yeah, and feel free to ask any questions about the system, the efficiency and security, etc. Yeah, thank you.
So there are actually two questions. First of all, thank you for the presentation. That was great. And Nuh just asked, maybe you can have a look at the chat.
So how the strategy is to better other competitors, like e.g. like polarization. Well, I'm assuming you're asking, oh, what's our advantage over the competitors? Well, actually, we're doing our best. We also read, well, from our side, we do our best, but we also learn a lot from their implementation. If you see the code base, you can see a lot of comparison. You can see some of the comparisons, and so for some of the components, it has our implementation also, and also other implementations with the name explicitly stated. Yeah, and next question, is there a ZK version of CUDA? Oh, it's not a ZK version of CUDA. Yeah, I just explained. I'm sorry for the confusion. I mean, at first I myself is confused about this as well. Yeah, it's actually organizing the proving system to better collaborate, like use this proving system for this one and that proving system for that one, and finally combine the proof. Yeah, that's true. Well, it's because it's a little similar to the CUDA execution, because you have host memory, diverse memory, and you have kernel launch, where the kernel refers to different proof system in our case. And you can probably you can launch them in parallel. Yeah. Thank you for the question.
While we're still waiting for more questions, let me quickly share the hacker pack in chat. Everyone, you will be able to find recordings and slides for all the presentations we've seen so far. Zhiyong, if you would be so kind to share the link to your presentation in chat, that would be amazing as well. We'll make sure to add it in the hacker pack so that people that did not manage to be here live will be able to follow through
Yeah, of course.
presentation afterwards.
Mm-hmm.
There's a new question from Nuh.
Yeah, efforts at standardizing across various ecosystems from. Oh yes. Well, yeah, I totally agree. I mean, in different languages and in different formats, circuits, R1C, etc. Well, we are trying. So we build our compiler system on the GNAC system, and I think our compiler would accept most language features in the GNAC system. So that is saying that you can write a circuit in GNAC and compile use our compiler. Most of the time it would work, but some of the features might not. I don't see too many efforts on standardizing the entire system. Will there be a Expander-based ZK virtual machine? Well, I think we worked on that a little bit, but then we somehow did not continue. Well, I think Zhiyong may know that better than I do. Yeah, let Zhiyong answer that in the chat.
For those of you watching the recording, the answer from Zhiyong Fang is that they are working and collaborating with a few partners to develop an Expander-based ZK-VM. And there will be a talk about it in week 6. This might be a good segment to just update you all that are being here for what's to come next. From early next week, we will actually start the building phase of the hackathon. So you will be able to start working on your projects. You'll be able to start working with the people you've teamed up with, or if you have not teamed up with anybody, now is the perfect time to do so. Make sure to go to your hacker pack. Make sure to look for the section of creating a team and forming a team. Look through the board we've created with all the developers that are available and looking to team up with somebody else, or just post in the Discord. Make sure to share a few words on what you're willing to build, what are your skills, what would you like to build, and hopefully just reach out to someone, say hi, get out of your comfort zone, and start collaborating with someone. We have 5 amazing bounties to build for, each of which has 50K of grants associated with them. So you will be having 4 weeks starting Monday to build for these tracks. There will be additional workshops, as Zhiyong Fang said in chat. We will be having more workshops, ideally in week 6. The speakers for which will be announced afterwards. They're still a secret, but we will try to organize additional workshops throughout the next week, which will be mostly focused on things to build and provide you some additional information on the bounties and the things that the Polyhedra team would like to see you all develop. Do we have any final questions, everybody? Link to the library and ideally to the presentation as well. That would be great.
Well, this is a proving system, and I would recommend to access it from the front-end compiler collection first. So the second one. There you can see an example of how to compile the circuit and run it. Yeah, thank you all for the good questions and attending our lecture.
Zhiyong, can you also share your slides, please, before?
Well, I don't have online version.
If not, you can send them afterwards, and we'll make sure to add them.
Yeah, I can send you probably afterwards.
Sounds good. Not going to be a problem. Right, everyone. Thank you for today's workshop. And do make sure to tune in tomorrow for the last workshop of the week and last workshop of the first 2 weeks of workshops, which is going to be on CUDA accelerated GKR prover, who's going to be delivered by Simon from Polyhedra. So again, this is not the end. We still have 1 more workshop to go tomorrow. So please have a look into your hacker pack, research the topic a bit, prepare a few questions, and we can discuss tomorrow. Wishing you all a great day. Thank you all for being here. And thank you once again, Zhiyong, for the great lecture. Have a great day, all.